Okay, so now this is where the chapter takes a bit of a step up in difficulty. So, we'll start off with this. This was actually, I think, meant to be taught before this bit, but we didn't really have to use it. Cos and sine can be expressed in terms of exponentials. And I guess you could literally just see it from here. Like, here, 2 cos theta, we know is z plus 1 over z. And we know that z is e to the I theta. So if we just want to find cos theta, you just multiply it all by a half. So you get a half of z, which was e to the I theta, plus e to the minus I theta. And that's equal to cos theta, so a half of that. And that's what we've got over here. So if you want to find cos of n theta, then you just multiply the argument by n. And then sine of n theta is just the same thing. Divide by, because you had 2i sine theta, you divide by 1 over 2i, and it's just the same thing. So I guess it didn't really have to be taught, but it's useful to know. Now, we can have complex series. So you know in A-level maths, when you've got like a geometric series, so like Sn is like a 1 minus r to the n over 1 minus r or something like that. And then when you've got the sum to infinity, that's just like a over 1 minus r. It's the same thing over here. If we've got a complex series, your a r to the n minus 1 over r minus 1 is the same as this. Your a is w, r to the n is z to the n minus 1 over z minus 1, same thing. And then when you've got your sum to infinity, where you had your a over 1 minus r, that's this, your w over 1 minus z. So this is literally just taking A-level maths, and now you're doing the series, the geometric series for complex numbers. But like A-level maths, the modulus, like your term in your series, has the modulus has to be less than 1, otherwise it will diverge and not converge. So that's what it says over here for an infinite series. So what it says is that the sum from r equals 0 to n minus 1. Now it's not n because we're starting from 0, this will be z to the power of 0, so you're just left with w as the first term. But there will still be n terms because you've got all of your z terms to z minus 1, to n minus 1, but then you've got this w over here. So there are still n terms in total. So that's why your n is like the number of terms. So it's to n minus 1, because that's when your power of z will be n minus 1. But then you've got this basically z to the power of 0 over here. So it just gives you n terms, so that's why you have n over here. So we can use these, and I guess use this fact to help us do things like this. So let's just get into this first one. So this was an example in the book. So we're given that z is cos of pi over n plus I sine of pi over n, where n is a positive integer. Show that 1 plus z squared plus whatever up to z minus 1, z to the n minus 1, is equal to 1 plus I cot of pi over 2n. What the hell? Yeah, I know how it looks. Okay, first we're told what z is. I guess we can represent this in terms of e to the I theta. So your theta is going to be pi over n. So you've got e to the I pi over n. I think that's, yeah. So 1 plus z squared plus blah 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 to z to the power of n minus 1 is this over here. So what we've got is a geometric series, which is your 1 plus z squared plus dot 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 plus z to the n minus 1. So we know that the first term, which is in this case w, is going to be 1. Your z is e to the I pi by n, and then your n is the number of terms which are, it's just n, because we had a dot dot dot, so we don't know how many terms there are. So therefore our sum is equal to w into z to the n minus 1 over z minus 1. So w was just 1, so what we've got is z to the n, which is, so z to the n minus 1 over z minus 1 is equal to e to the I pi over n raised to the power of n minus 1 all over e to the I pi over n minus 1. So what this gives us is e to the I pi minus 1, because when we multiply the indices, n and over n will cancel, and we're over e to the I pi over n minus 1. Well, we know Euler's formula, e to the I pi is minus 1. So we're just going to get minus 1, and then this minus 1 over here. So we're going to get minus 2, all over e to the I pi by n minus 1. Right, now, this is where I guess it becomes harder, because you have to do some manipulation over here. So we've got the minus 2 over here. Now, like I said over here, you can represent cos and sine of n theta in terms of, like, complex stuff. So, here we've got e to the I pi over n minus 1. We've got this minus 1 over here, so clearly we're going to be using this one. We're going to try and turn it into a sign, because here we've got a plus, here's the minus, so we want to try get this. So because we've got minus 1, we want to try make this minus 1. So how can we make that minus 1? So we need inside the bracket like e to the in theta minus e to the minus in theta. So we have to make this minus 1 and like manipulate it to get minus e to the minus in theta. So if we try and manipulate this, so this, how can we get the powers to be the same? We know that minus 1 is e to the I pi. So what we've got is e to the I pi over n plus this. Now these are almost the same. We've got e to the I pi and e to the I pi, but we need to get an over n over here. So I think what we can do is if we factor out half of the power, so if we get I pi over 2n, here we're going to get e to the I pi over 2n, because then when we multiply it together, the indices will add together and we'll get this. But now if we add it to something, we want to get e to the I pi. So what is that something? Well, we know that e to the I pi is minus 1. So we want to get this times something is minus 1. So what we can do is put a minus here instead, and then we just need to get this times something is 1. Well, to get it something is 1, we just need to multiply by e to the minus I pi by 2n. So minus e to the minus I pi by 2n, because then the powers will cancel out. Well, look at this, we've got the same thing over here now. So what we've got is e to the in theta minus e to the in theta, where in theta, which is I times pi over 2n. So this is equal to e to the I pi by 2n into e to the I pi by 2n minus e to the minus I pi by 2n. Well, let's try to get rid of this now. So if we multiply both sides by e to the minus I pi by 2n, this and this will cancel, and then we'll get this on the top. So minus 2 e to the minus I pi over 2n, and then we're just going to be left with what's in the brackets. So e to the I pi over 2n minus e to the minus I pi over 2n. Well, we said that sine of n theta was equal to 1 over 2i times this, but we've not got the 1 over 2i anywhere. So, like we said earlier, 2i sine of n theta is just going to be what's in the brackets. So we can write it in terms of sine now. So we've got minus 2 e to the minus pi over 2n, so minus 2 e to the minus I pi over 2n, and this is all over 2i sine of pi over 2n. Well, look at this now. 2 and 2 cancel, so we'll be left with minus e to the minus I pi over 2n all over I sine of pi over 2n. Well, we can get rid of the I in the denominator by multiplying by I over I. So that's just going to give us I e to the minus I pi over 2n all over I times I is minus 1, so we'll get minus 1, but then that minus at the front will cancel. So what we'll be left with is sine of pi over 2n. Right, well, we want to show that the thing is equal to 1 plus I cot pi over 2n. Well, to get cot, we need cos over sine. Well, we need cos in the numerator, so what we're going to have to do is convert this into modulus argument form. So what we're going to get is I into e to the minus I pi over 2n, so cos of I pi over 2n minus sine of I pi over 2n. Nope, we're not going to have an I in there. The I is going to be here. And that's over sine of pi by 2n. So hopefully now you can see that it's going to cancel. I and I will make minus 1. Sine and sine will make the 1. Cos and sine will make the cot. So we're basically finished now. So multiply everything by I, multiply out the brackets, so we're going to get I cos pi by 2n. And then we're going to get I times minus I, which is minus minus 1, which is just 1, so we're going to get plus sine of pi by 2n all over sine of pi by 2n. Now because they wanted it in 1 plus I cot blah blah blah, this will be our 1, this will be our I cot. This is equal to 1 plus I cot of pi by 2n. Boom! I'm pretty sure you can see the difficulty increase. So yeah, trust me, this is not easy. Even I'm not finding it easy. But like everything, practice makes perfect. So I'm actually kind of glad I did this now. Like, there's still more to it. There's still like roots of unity and stuff like that. But I'd probably say that this, all the like the manipulation and things you have to do, just make it hard. Like, you have to actually like think about what you're doing. It's not just formulaic. Like, you can't just memorize this and use it for everything. You have to think about what you're doing. But I mean, of course you do, because it's further maths. You should be like good at math. You should like math, so it should be fine. So anyway, keep practicing. Hopefully this made sense. If not, I will try and probably make more videos explaining better or just doing more questions. So yeah, so we will now be going on to nth roots of a complex number and the roots of unity.